Hi everyone, my name is Caroline Yu and I'm from the Electrical Engineering Department at Columbia University. Today, I'll be presenting our work on tip tracking of surgical navigation stylets using integrated strain sensors. I'll be reviewing our system from device design and fabrication to characterization. Let's dive right into the motivation for this project. Surgical navigation is the action of neurosurgeons using tracking tools to remove often benign tumorous tissue. Typically, flexible catheters are used to remove the tissue and navigation stylets are used to guide the catheter. Placing these catheters requires precise placement of the navigation stylet, and there are various technologies that exist to track the stylet as a whole entity. The top picture shows an example of white matter tractography, where tracking modules are placed on the handle area of the stylet, and the stylet is modeled as a rigid entity. However, it's been found that brain tissue often applies force to the tip of the stylet because the stylet is often thin at 1 to 2 millimeters in diameter. The pressure causes the stylet to bend and the tip location is therefore lost. So our goal here is to track the stylet's bending as well as the tip location. Previous methods to track stylet location include optical force sensing. So I'd like to highlight two previous works. One, done in 2019, consisted of an optical slit that moves with respect to an IR LED bicell pair. This system allows for tip tracking down to tens of microns, but requires a large shaft diameter. As you can see here, 8.3 millimeters. So this is not useful for neurosurgery, and it also requires a full design of these stylets. Another design that was presented in 2012 consists of a tip with a Fabry-Perot cavity and uses optical coherence tomography to track axial and lateral force. The system we are proposing allows the device to be attached to any navigation stylet at its base end. Here's our solution to navigation stylet tracking. It consists of strain gauges wrapped around a navigation stylet that tracks the stylet bending in two axes. On the right, you can see a picture of the strain gauges wrapped at the base end of the stylet, so that when force from brain tissue at the stylet's tip causes the stylet to bend, the strain gauges are strained and therefore their resistance changes. These sensors consist of patterned silver on flexible PDMS and are placed on a 1.3 millimeter diameter navigation stylet using an adhesive stack. The signal readout is performed by connecting a flexible heat seal connector, which is also connected to source measure circuitry. Overall, the key requirements for our device are precise sensor placement, high sensor sensitivity, and good device adhesion to the stylet. Here's our strain gauge sensor design. The sensor consists of patterned thin film silver on PDMS, and the design consists of 4 strain gauges that are serpentine structured to provide a high base resistance in a small surface area. The base resistance is calculated using the equation shown here, where R is the base or unstrained resistance, Rho is the resistivity of thin film silver, L is the total length of the strain gauge trace, T is the thin film thickness, and finally W is the serpentine trace width. So for example, our fabricated device has a total trace length of 16.5 centimeters. The trace metal film thickness is 60 nanometers, and the trace width is 25 microns. So that means each strain gauge has a base resistance of 3.3 kiloohms over a surface area of 14 squared millimeters. Topology-wise, when the device is wrapped around the stylet, one pair of strain gauges covers one quadrant of the stylet circumference, as you can see in the bottom right figure. The other pair of strain gauges is placed on a quadrant translated 90 degrees from the other quadrant. So you can see these two sections are highlighted in blue and represent tracking the directions in X and Y. If we look along the length of the stylet, there are also two pairs of strain gauges that are used to track strain along two different sections of the stylet. Lastly, electrode contact pads utilize four-terminal sensing and are placed perpendicular to the length of the stylet so that we can eliminate connector delamination. To fabricate the device, first a glass carrier is cleaned, treated with UV ozone plasma, and exposed to a fluorosilane and a desiccator as an anti-adhesion monolayer. Then 70 microns of PDMS is spin coated onto the glass and cured. 60 nanometers of silver is then thermally evaporated, and positive photolithography is used to pattern the silver. Once the device is done being fabricated, to laminate the strain gauges, the PDMS is peeled off of the carrier glass wafer and placed on a polymer-sized silicon gel adhesive. Then this stack is placed on top of a 3M acrylic double-sided tape, and this entire stack is then aligned and rolled onto the navigation stylet. Because the adhesive strength is important for durability and device uniformity, pull-off strength adhesive testing was performed to determine the adhesive strength of various adhesives to PDMS as well as the stainless steel stylet. Various options include a double-sided silicon gel adhesive, or polymer science 1829, has a thickness of 180 microns. Another option is double-sided with silicon gel on one side and acrylic adhesive on the other side. What we found from the pull strength test is that a combined adhesive stack of silicon gel plus a 3M double-sided acrylic tape was the combination with the highest pull strength of 1.33 newtons per centimeter, whereas the double-sided silicon gel and acrylic polymer science tape had a pull strength of 1.18 newtons per centimeter. Once the strain gauges are laminated onto the stylet, the stylet's bending and tip displacement from the unbent position is found using a cantilever beam deflection model. In this model, Y is the displacement of the stylet, F is the applied force at the tip, E and I are material properties of the stainless steel rod, X is the position along the length of the rod, and L is the length of the stylet. So for example, with a bending condition of 0.1 newtons of force placed at the tip, we see that the stylet bends on the left side of the graph. What's more important to highlight is that the slope of the stylet is greatest near the base end of the rod. So this means that by placing the strain gauges at the base end, we can provide the maximum amount of bending induced strain. Also, placing the strain gauges at this location limits contact of the strain gauges with any brain tissue, since the device is to remain outside of the brain throughout the entire surgical procedure. From the electrical readout side of things, it was necessary to use averaging to reduce voltage readout noise. Typically, moving averages can be used to reduce random noise, but the slow roll-off in the frequency domain is not optimal for low-frequency signals. And so we used exponential moving averaging to eliminate high-frequency noise as well as summing noise, since we are reading the voltage across various strain gauges. This enables our noise floor to be 4.3 millivolts, which corresponds to 250 microns of tip displacement. To characterize the system, the change in strain gauge resistance was related to bending induced strain. So by knowing the change in resistance in the gauge factor of the device, the bending induced strain can be calculated, as seen in this first equation. From there, the applied force and tip displacement of the stylet can be calculated. And so the only thing we need to know is the gauge factor. And so in order to calculate the gauge factor, various amounts of strain was applied. to the strain gauges, and the change in resistance was recorded and then normalized with the base resistance of each strain gauge. The gauge factor of the device was found to be 1.5, and when we compare this to the gauge factor of this same device placed on a planar PDMS surface, the gauge factor is slightly lower. Overall, with our noise reduction techniques, the devices we fabricated have a limit of detection of 0.75 millimeters and demonstrate linear behavior up to 9 millimeters in tip displacement. In general, our device has higher sensitivity than what is possible with flex PCBs, which typically have a 100 micron wide trace limit and are typically on a polyimide substrate. Lastly, with the strain gauges placed on orthogonal quadrants, we are able to show separate tracking for X and Y with low cross-axial noise. And so our next steps are to integrate this device into existing navigation systems. Overall, we have presented a system that provides tip and stylet tracking for neurosurgery navigation procedures without interfering with current navigation technology. Second, using our elastomer substrate allows for an improved limit of detection of 0.75 millimeters, but does have a lower durability than polyimide. Lastly, we found that a 2-layer adhesive stack of silicone adhesive and double-sided acrylic tape provides for a high pull strength of the strain gauges on PDMS to the 1.3 millimeter diameter stainless steel stylet. We think that this device is the beginning of using mechanical sensors to track small amounts of movement on thin objects, for example, 1.3 millimeter diameter rods, without the need to fully redesign tracking tools. With that, I'd like to thank the CLUE Research Group for their help, as well as Synaptive Medical for their funding, and lastly, Columbia's nanofabrication facility for their help. And with that, I'd like to take any questions.